Hello everybody, my name is Dmitry, I'm the moderator of today's talk, and today Justus Calvin is going to present his work on tiled arrays. He's from Virginia Tech, so Justus, please go ahead.
All right, thank you. My name is Justus Calvin. I'm a graduate student in the Vallejo group at Virginia Tech. And today I'm going to be talking about tiled array, which is work I've been doing for my thesis for the last 4 years. So anyway, I'm going to cover some of the motivations behind tiled array, why we're doing it, then some of the background, what's been done in the field, what are the important issues with tiled array, and then I'm going to move on to sparse distributed tensor algorithms, kind of discuss why they're important, how we implement them, and then finally I'm going to give some examples about how to use tiled array and what the code would look like. And lastly, I'm going to be showing some benchmarking data. So we're primarily motivated to look at couple cluster type equations. In this equation you see on your screen is the couple cluster singles and doubles T1 amplitude equation, and it consists of a series of matrix multiplies and tensor contractions that are summed. And most of our work most of the equations that we deal with are going to look something like this. So for example, you're going to see like a second order tensor times second order tensor, fourth order tensor times the second order tensor, and fourth order times fourth order, so on. And we have to write all these equations in code, and it can be quite complex and time-consuming. As you can see, there are quite a few equations. More complicated theories have a lot more terms in them. So what would we expect if we were going to write something like this in code? If we look at just the last term of the equation on the last slide, we have a fourth order tensor multiplied by fourth order tensor multiplied by second order tensor, and we're summing over the indices KLCD. So if we were going to program this in a simple serial code in C++, you'd have 6 nested loops, and on the inside you're going to do an element-wise contraction from these 3 tensors and then sum them into the term 14 here. And this can be quite challenging to actually debug code, especially if you have many terms that you're dealing with. It could be hundreds of lines of code just for the equation that I showed you on the previous page. But what we want to do is something that's a little bit more readable and a little bit easier to understand, and something that fits more closely with the original equation. So the code here on the bottom is what it might look like if we wrote the loop structure in tiled array. So here we have our integral fourth order tensor, which is equivalent to this term here, multiplied by your T1 and T2 amplitudes here and here. And this is a lot easier to read than something like this. And this is just a simple serial code. If we wanted to make it run fast, then it would probably require, this one term might require 20, 30 or more lines of code, and it could be thousands of lines of code for a large series of equations. If we want to actually do this in distributed memory systems, then it could require many thousands of lines of code just for this one equation. And editing and modifying this type of equation can be challenging, especially if there's an error where you may have transposed 2 indices, for example. They all look the same, so which one is right? So a lot of work has been done in this area to try and help us out with writing code for these types of equations. We have parallel matrix multiply libraries like Blocks, Flame, and Elemental. These work fairly well, except they're not really well suited for tensor arithmetic because we have to always rearrange our data so that it fits a matrix layout. So what we actually want are more tensor-based libraries like Tensor Contraction Engine, Sail, CTF, and libtensor. All of these libraries use kind of a language similar to what I showed on the previous slide for TiledArray, that you write code that looks very much like the expression that you're trying to represent in the code. TC is probably one of the most well-known of these, and what they do is they take this expression and generate code based on the expression that you've entered. Sail does something similar, except they have their own entire language. CTF and libtensor both use expression templates in C++. So all of these libraries are mainly concerned with tensor contractions, and the reason for this is that they represent the bulk of the work that you're going to be doing when evaluating all these tensor expressions. So what does a tensor expression look like? Here I have just a simple A times B tensor expression, and then we're storing the result in C. And we're summing over the indices K, K1, K2, etc. And the resulting tensor will have indices M1, M2, N1, N2, and so on. So we can recast these matrix or these tensor operations into matrix operations by combining the indices M and K and N and recast it into this simple matrix multiply. We may need to actually permute the data to do this internally, but the tensor libraries try to handle permutation of the data automatically so that the user doesn't have to worry about it. So we're also interested in distributed libraries, so we can do very large calculations. And the question arises, how do you actually partition the data of your matrices or your tensors? One thing I forgot to mention is since these tensors can be remapped into matrix multiplications, for the remainder of the talk I'm just going to talk primarily about matrices and use matrices as examples. And all the information will apply to tensors as well as matrices. So one works just as well as the other. Anyway, going back to where I was. Distributing tensor data. So here I have two tensors that I want to contract, and I've partitioned the data by row among 16 different nodes. And what do we have to do if we want to actually contract these? How do we move the data? So if we look at just the first row of matrix A right here, we have to distribute part of the data for row, the blue row, to every node in B here, shown in red. And if we extend this to all rows, then it becomes an all-to-all communication type algorithm, and that is definitely not scalable. So what we want to do is actually partition the data more into a block type format or a grid. And this is a much better way of actually representing the tensors because it minimizes the overlap of any individual block from A onto B. So if we're going to do a tensor contraction with this data layout, this one block here needs to be distributed to these 4 nodes on B. And the same is true for every block. We only need to send each node only has to communicate with a small subset of other nodes. And another advantage to this is that we can very easily map blocks to elements when we're dealing with our distributed algorithms. So we can treat one block as an element that we move around, and we don't have to worry about the actual list of numbers that are contained in each block. The other reason that we want to use blocking structure is because it fits the physics of our problem, and I'll talk more about that later on in the talk. So the main algorithm that we use for distributed matrix multiplication is the SUMMA algorithm. Stands for Scalable Universal Matrix Multiplication Algorithm. Imagine that we have two tensors that are blocked, A and B, and we want to store the result in C. So we're going to set up a grid of C among 16 nodes here in this example. And we're going to iterate over columns of A and rows of B. So there will be K columns and K rows. For each step, we're going to take one of these columns and one of these rows, and then we're going to broadcast each block along the row of C for column AK, and we're going to likewise broadcast each block along a column of C. So the result at each step is that each node of C will have one pair of A and B, and it will perform an outer product and sum that into its local copy of, or local portion of C. The nice thing about this algorithm is that it has very regular communication patterns and uniform data distribution. So by design, it has even, by design it will have, sorry, I lost my place. By design, it will have even computation on every node at every step. So we don't have to worry about scaling up as we go to larger and larger matrices, because it very naturally distributes the data and very naturally distributes the computation. So the design goals that we had for TiledArray were to help us implement new many-body electronic structure methods. So what do we need out of a tensor library to do this? We want something that we can easily compose block structures. We want to have replicated and distributed memory tensors, and we want to have distributed computation so that we can easily work on both small and very large systems. We also need a high level of abstraction so that we can quickly move from equations that we're working on to actual working code. And actually implementing the code tends to be the biggest bottleneck in what we do. So anything that can speed up the implementation and testing of these codes will help us be more productive. So we're interested in sparsity for obvious reasons of reducing the amount of communication and computation that we're doing. And if you look at what's available right now as far as sparsity in distributed systems, most of it is centered around full sparse matrix multiplication. In the first example here, we have a matrix times a vector. So we partition the data by columns and rows so that we can easily move X down columns of A and sum across rows to give us Y. Similarly, we have sparse matrix multiplication. Here, the common method for this type of computation is to use sparse matrices as your blocks. So it's very similar to your SUMMA algorithm, where instead of moving dense blocks of data, you're actually moving sparse blocks of data, and you're performing contractions on those sparse blocks for each node of C. The problem with these methods with sparse blocks is that the communication time tends to grow much faster than the computation time with these types of matrices. So for small matrices, you can overlap communication with computation, but when you start scaling up to large distributed systems, the communication becomes the major contributor to your time, and the computation becomes a very small fraction. So it's just really not scalable beyond a certain point. In the paper, I think they said were able to scale their test benchmarks up to about 1,000 nodes. So for our work, we want to try to do block sparse. And the reason we want to do block sparse is because the data that we're working with in our problems tends to be clustered. So we have clusters of non-zero data and clusters of zero data. And we're going to be using irregular tile strides as opposed to other methods which typically use very regular strides so that they can have even amounts of computation and communication. And the reason we use irregular strides is because we want to exactly fit the data that we're generating from our problem. We're also using unstructured sparsity because the sparsity patterns that we're dealing with, while there is structure, it's not really clear, especially in high-order dimensions, what that structure is or what it should be. And the advantage of using block-sparse data structures are obvious. We don't have to store zeros, we don't have to compute zeros, and we don't have to move zeros between nodes. But the more important reason that block sparsity will help us is because we're able to do dense calculations and we're able to do high-density data movements. So we can take advantage of the performance of dense matrix multiplies and moving dense data. And we also get to take advantage of the sparsity at the same time. And it won't suffer from the problems of moving very small amounts of data between nodes at every step. And I'll go more into detail about how we're going to do this. But first, let me talk about some of the parallel runtime that we use in TiledArray. It's based on MADNESS, which is numerical scientific simulation software. And the approach there is to use global objects to represent data. Global objects, in our case, would be tensors. So each tensor has a local representation on a compute node that is used to compose tensor contractions or other expressions. And it also has task-based parallelism, which allows us to decompose the problem of computing tensor contractions or other tensor operations into small, manageable chunks. And I'll show more about this also later. And finally, it has active messaging. And active messaging is similar to point-to-point messages in MPI. The difference is that in addition to the data that you would have in a point-to-point message, an active message also passes a function to the receiving node. So you could think of it as one node sending a package of data and a function saying, here's data, here's a function, run this function with the data. And the sending node doesn't have to worry about whether or not the receiver is ready for it, and the receiver doesn't have to wait for the sender to send a particular piece of data. You just send it and forget about it. And wait, eventually the receiver will do the computation and send the result back to the sender node. So task-based parallelism, as I said, allows us to decompose the problem of doing tensor arithmetic into small manageable pieces. So consider this small program here where we're taking a global object A, which represents our tensor, and adding it to another global object B, and then storing the result in C. So if we're going to add the tiles, we need to first construct tasks. So each node has a little bit of data. In this case, tiles 0, 0 are on node 1. And it's going to submit a task that will sum the two tiles and then store it in a predetermined location for tensor 0, or tensor C. Similarly, it's going to also spawn the task for computing tile 1. In this case, though, tile 1 is located over here on node 2. So we need to move the data to node 0 or node 1. Once the data arrives, we can perform, the task queue will schedule the task for computation and then place the result in 1. Now 1 is going to be stored on node 2, so we then send it back. Here, when we're computing tile 0, it's actually stored locally, so we just store it in the local representation. And we do this across all of the nodes. Each node will compute a subset of all the tasks necessary to compute the sum of A and B. So now let's consider using a sparse SUMMA algorithm. If we have a tensor A and it's missing some portion of its data due to sparsity, let's say this tile right here is 0. We don't actually want to send any data or compute any data for that. So for iteration k where this tile is 0, we're not actually going to broadcast this tile. We're still going to broadcast this tile across this row and these tiles across these rows of C. And similarly, we're not going to broadcast the tiles of B to the nodes that aren't going to actually do any work. Unfortunately, this kind of algorithm doesn't work very well because SUMMA relies on the fact that all the nodes have roughly the same amount of work and the same amount of communication. Now we've got a situation where we have a quarter of our nodes doing nothing for one iteration. And if we have more tiles that are not present, then we have more steps in the algorithm that are not going to actually be computing any data. So how do we address this? In our code, we use a task-based SUMMA algorithm. And what we do to modify the SUMMA algorithm is we break it up into tasks, similarly to the task of adding two matrices together. We're going to break up SUMMA into its basic component tasks. So the tasks that we use are broadcast or columns and rows of A and B, and we're going to have tasks for contraction, and we're going to have tasks that actually schedule the contractions. The advantages of these approaches are that we remove the explicit barriers that you would have between each time step. So the barrier in the standard SUMMA is the broadcast of the rows and the columns of A and B. But here we don't have to actually have those barriers because we compute when data arrives, and we control the overall computation by controlling how the data moves and when based on task scheduling. So another advantage is that since we've removed the requirement for barriers between iterations, we also are now allowed to overlap iterations. So, for example, in the previous slide where you have data that's not moved, data that is not present in one tile or another, we just skip over it. So if you're computing K2 and then K3 isn't present for that particular node, then you just skip that and go on to K4. So you can have multiple iterations of K being computed simultaneously on one node and on different nodes. And this is possible because we've broken up the tasks into their basic components. The other advantage is that we offset the load balancing issue to the end of the algorithm. So if we just skip the individual contractions that are zeros, all the nodes are going to be skipping all the contractions that are 0. And on average, as long as the number of contractions that each node has to compute is approximately equal, then we should have even load balancing across our entire network. We can take this a little bit further when we're evaluating expressions, and we can break up each of these operations in a tensor expression into a series of tasks. So the way we actually evaluate expressions in TiledArray is we first start out with the evaluation of a summation for summation of A, B, and CD. This then spawns more tasks that evaluate A and B, and respectively C and D. And those tasks also spawn more tasks to evaluate their arguments. So the kind of evaluation you might do on a single tensor would be to scale it or to permute the data so that it's ready for the contraction for a subsequent expression. Once all of these tasks have been constructed, then we start constructing the individual evaluation tasks for the tiles. So all the tiles of A would be constructed in these tasks here, and the tiles of B would be constructed here, and so on. These tasks then feed more tasks, so here would be our contraction tasks for A times B. And we can actually start computing some of A and A times B while these tasks are being evaluated. So if a few of A and a few of B are ready, we can start doing contractions. Similarly, we can do on a separate node or on the same node, we can start evaluating C and D, and also part of C and D while A times B is being evaluated. Oops. Sorry about that. All right, and then once these tasks start to be evaluated, then we can take the results of those tasks and finally stuff those into another set of tasks that sum the results of our two contractions. And finally, those results are placed in the result tensor. Now, the nice thing about this is that we can actually have multiple pieces of our evaluation going on simultaneously. We could be evaluating A while we're doing contractions of B elsewhere, or excuse me, a contraction of C times D. And we can actually string all these contractions and additions together. And load balancing is only taken care of at the end. Again, we want to try and distribute the workload evenly, so any of these tasks could be missing, for example, and because the actual tiles are 0. And similarly with the SUMMA algorithm, you don't have to worry about which tiles are missing, which tiles are not. As long as we keep the task queue busy with enough tasks, then we don't have to worry about pauses in computation. So the types of tensors that we're going to support in TiledArray, or we do support in TiledArray, are dense blocked containers. So we have dense tensors. We have block-sparse tensors, where we don't store any actual data for 0 tiles. We have direct method tiles. So these are tiles where you have an empty container, and whenever you need data for that particular tile, the container will generate the tile's data, use it in computation, and then throw it away. So this would be advantageous for four-dimensional integral tensors, for example, where the storage requirement might exceed your actual how much memory you have on the machine. So we only want to produce tiles as needed. We also have replicated tensors. So if your tensor is very small and would fit in memory on all of your nodes, then you can also do that. That would further reduce the communication of our algorithms. So now I'm going to show you a little bit about how we construct TiledArray objects and how we use them. So the first step is to construct tiled range. And tiled range just represents the tiling structure of our tensor. In this case, I'm constructing an array starting at 0, and we're going to have tiles that store at least 10, store exactly 10 elements, and we're going to have 10 of those. So this array represents a tile that goes from 0 to 10, or excuse me, 0 to 9. This one would go from 10 to 19, 20 to 29, and so on. And we would then construct a 4-dimensional vector, or a vector of 4 tile 1 range objects that represent a 4-dimensional tiled range. And then we just pass these an iterator with each of the different boundaries that we're going to use for our tile. And the final structure of this would be a set of 4 arrays that contain the boundaries for each of our tiles. Once we've constructed the tiled range, then we go on to construct the actual tile or tensor objects. So here we have an array that stores double elements and has 4 dimensions. The arguments passed to it would be a world object, which is the madness equivalent of COM world in MPI, and then the tiled range that we constructed in the previous slide. Sparse arrays are constructed very similarly to dense arrays. The difference is that we have to supply a shape object, or a list of tiles that are going to be present or non-zero in our array. So in this example, I'm constructing a shape where every 5th tile is non-zero. You don't have to actually construct or list every single tile that's going to be present for your array on every single node. Instead, what you can do is you can compute just a subset of the range, or of the shape, excuse me. So the idea is, if you are doing some kind of screening technique where you're trying to decide whether or not you want to store a tile that's near 0, well, you could compute the norm of that tile, for example, or estimate the norm of that tile, and then decide on that node whether or not you want to store it. And you can do this for every single node, and that way you don't have to recompute which tiles is 0 and which tiles are not. When you construct the actual array with your local list of your shape, then it would broadcast that data to all other nodes so that every node knows which tiles are 0 and which tiles are not 0. So next, once we have our tiles or our arrays initialized, we want to fill it with data. So here we're going to create tasks to evaluate our individual tiles. So from the main thread, we would have an expression that looks like this. So we call the madness task queue to create a task, and we call the task make tile. And then we're going to tell it what the dimensions are of that particular tile. Now, when you construct a task, it returns immediately without doing any work, and just returns a location of where the result of this task will go once the task has been run. We use this future tile to fill our array. So we tell it which index the tile has and where the data will be once the computation is complete. So down here I've shown a very simple task function, what a task function might look like when you're filling in data for an individual tile. So we construct a tile, we fill it with zeros, and then we return the tile from the task function, which then assigns this value here. And we do this for every tile that is local to our data. One thing I forgot to mention was that we don't want to actually repeat this work for every node, so we provide a convenient iterator that allows you to iterate only over the local tiles for this node. So I could put this in my main thread without any statements, and every single node would compute a different set of tiles that would eventually go into our array. And these indices are guaranteed to be unique for each node. So the mathematical operations that we are targeting are addition and subtraction, contractions of tensors, scaling of tensors, vector dot products of tensors, the 2 norm and the infinity norm. And also we support arbitrary expressions, as you've already seen. We also support user-defined functions and user-defined reductions. So let's say you need to do the norm 1. You can implement it using some of the same machinery that we use to implement the norm 2 and the norm infinity inside TiledArray to do your own reduction. Or you could do a reduction where you sum all the elements of a single tile or set of tensors. In addition, we support user-defined functions. So if you have some special modification that you need for a tensor or some sort of special purpose function, you can easily adapt the existing code to write your own expressions so that it would look something similar to this dot function or a norm2 function. You can also do binary operations. So if you want to define a wedge operator to do some crazy expression that you think you need for your library, you can do that. So here's an example of a code that another student in our group wrote, which is a density-based Hartree-Fock code. And here I've just shown a portion of the SCF loop. And this is actual working code. So each of these expressions you see here and here and here represent calls to TiledArray objects and are evaluated in parallel. And writing something like this should take no more than a few hours to get something basic working if you have all the equations available and ready to go. So if we look at each of these equations, you can see how they very closely match a mathematical expression. So we're assigning G here based on Q times D times Q, and likewise Q times D times Q. And if you'll notice that the indices for these objects are different each time they appear in this expression. So QPQ is used 4 times in this expression, DAO is used twice. But the indices for each of these are slightly different. And it just uses the data, the same data for the computation of G, but it combines them in different ways. It sums over different loops, or sums different elements in the loops. Here we have the Fock matrix where we're combining H plus G. And similarly, we have the gradient, which is used for the DIIS error calculation. So here this looks like a small matrix multiplication, or looks like a series of 3 matrix multiplications, take the difference, and then multiply it. And then finally, we have the energy calculation at the end of our loop. Here we have some DIIS solvers which help the Fock matrix converge more quickly. And it's kind of similar here. We just have a density update function, which I mentioned you can write your own functions to modify these tensors. And inside here we have a whole series of equations that use F and S to modify D. And then the last step of the iteration is to do a fence, and that's just to keep all the data in sync so we don't go too far. Otherwise these expressions might start evaluating multiple at a time, so you would be calculating possibly 2 or 3 Gs all at once. So at the end of each iteration, we check for convergence and then exit and do our energy calculation. So now I'm going to show some benchmark results from TiledArray doing a simple matrix multiply. So here we started out with 32 nodes on Vesta, which is a IBM Blue Gene Q system. And we did a variety of different tile sizes, starting from 128 by 128 going all the way up to 512 by 512. And we used 2 different matrix sizes. So this set of data here on the top represents the timing measurements for the 65,000 by 65,000 matrix. And the bottom 3 represent the timing measurements for the 32,000 by 32,000 matrix multiply. And we scaled this all the way up to 1 full rack of Blue Gene Q. The data, or the times actually go down quite significantly as you increase. And you can see the speed up here on the next slide. So the best performance was the smaller 65K by 65K matrix multiply. If you notice this one down here, the 512 by 512 for the 32K by 32K doesn't seem to scale very well. It levels off right around 256 nodes. And the reason for this is because it's actually running out of parallelism. There are not enough tiles per node for you to actually be able to use all the processors on every node. Whereas here we have a lot more tiles that we're actually computing simultaneously, which is why it scales to much better speeds. And finally, we have the single node matrix multiplication scaling test. So here I was just testing to see how the number of threads affected the speed relative to the tile size. So the bottom axis is going from very small tiles. I think this was 16 by 16 or maybe 32 by 32 tiles, and scale it up to tiles that are 1,000 by 1,000 elements. And on the y-axis, we are scaling up. We're going up from 2 threads all the way up to 64 threads, which is the maximum number of threads we can have on Blue Gene Q. And the speed, the top speed here was a 512 by 512 tile with 64 threads. And this was a little over 100 gigaflops, which is about half of the machine peak. And from what I'm told, this is about as good as you can expect using the BLAS implementation on Blue Gene Q. And finally, I was doing a task trace as part of my optimization of these on our local cluster here at Virginia Tech. And what this is showing is a series of 5 matrix multiplies. So you can see the barrier between each matrix multiply by this dip here, 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 and here. And this dip is just because of a barrier that I placed between each iteration of the matrix multiply. So this represents an entire matrix multiply. This leading red represents tasks that are redistributing our data. So we want to take tiles that are input in one data layout and move it to another distribution among the nodes. And this is required for performance reasons in the SUMMA algorithm. The y-axis of this chart shows the number of the average number of tasks that are computing these tasks for each time step or time slice. So here we're showing 100 total time slices, and each time slice can have up to 8 tasks running simultaneously. The blue tasks, which dominate the matrix multiply, are the contraction tasks. The yellow area shows tasks that are running broadcast send. So we're sending data from one node to another node in these. And the green tasks represent the receiving end, which are so small you can't actually see them. And the main takeaway message from this top chart is that most of our time is spent doing matrix multiplications, and it stays very level all the way across while we're doing the matrix multiplies until we reach the end where we actually run out of work and the matrix multiply ends. But this is only for a few small time steps. This represents a fraction of a second for each time step. This bottom chart is similar to the top chart, except I'm just showing the number of running tasks versus the number of pending tasks, how many tasks are ready to run but not actually running. So again, you can see that the number of tasks that are running at any given time when doing the matrix multiply is very close to 8 for the entire time. And as long as we keep this blue line, which is the pending task, above 0, then we will have basically full speed for our matrix multiplies. You can see kind of what happens when we run out of work. Here at this top, we had a spike of work and then ran out of work while we're doing the data redistribution, and then we get more work, and all of a sudden it pops back up to 8 tasks all running simultaneously. Again, at the end, you can kind of see it running out of work. Here, we're almost out, and you see that the number of tasks that are running simultaneously goes down as the pending work goes down. And this just shows that we are actually load balancing at the end and not having to worry about load balancing issues too much in the middle of our matrix multiplications. All right, and finally, future work. Right now, I'm mostly concentrating on implementing and optimizing the Block-Sparse Tensors algorithm. I'm also working on 2.5 matrix multiply, which is a method for speeding up our dense as well as sparse matrix multiplies with SUMMA. I want to also implement non-permuting tensor contraction operations. So I mentioned at the beginning that we would, if the data in our tensors don't match the matrix multiply exactly, we need to rearrange the data. This project right here would allow us to avoid the step of actually reorganizing the data. Another to-do item is to map the data layout or the layout of blocks to the topology of blue gene Q. Right now, we actually don't map at all to the topology of the blue gene Q, and most algorithms require it to achieve top speed. We're actually scaling very well, despite the fact that we aren't matching the topology and our communication patterns don't match the topology. I'm also working on compile time expression optimization. So what this would allow us to do is at compile time reorganize small expressions. So for example, we might be able to factorize a small expression. Finally, symmetry support. We are looking at implementing different types of tiles in our implementation so that we can take advantage of symmetry within a tile and within the tensor. And finally, we're looking at implementing tiles that are fully sparse, but only if needed at some point in the future. Right now it looks like dense tiles will probably work for most of our needs. And with that, I'd like to thank you for your attention, thank my group, all the people who have contributed to Madness, the people at Argonne, and of course the people who pay for all this research.
Okay, thank you very much. Okay, thank you very much, Justus. So if anybody has any questions, please write it in this chat in the questions section. And actually, yeah, I have one question. So did you try to benchmark your code, your library with some quantum chemical methods like CCSD, or I don't know, did you look at it, how well it works with some?
No, we haven't gotten to the point where we're able to benchmark this library with CCD applications. I did write a very stupid, very slow CCD application as a proof of concept to see if I could actually solve a CCD problem with the tensor library. The density-based Hartree-Fock code is actually one of our first steps towards evaluating sparse tensors or working towards evaluating sparse tensors. But no, we haven't actually done anything with couple cluster yet. That is one of the directions that we will go to in the near future, though.
Yeah, I see. But like your results on matrix multiplications, they look indeed very promising for applications and quantum chemical methods. Yeah, and also I have another question. So basically, I think it's the very common problem in the modern computer science when you try to do some massively parallel computations. You basically spend more time on all this communication stuff because you need to move data from one node to another node, compute it there, move it back. So can you estimate how much time will it actually take to what's the actual amount of time will it take to move data and to compute on some really parallel stuff on the blue gene?
I haven't actually done any of the calculations for that, but the data movement for our SUMMA algorithm, at least the dense version, is basically the same as it is for your SUMMA algorithms written in traditional MPI and BLAS and using other code methods. But the idea for our library, and one of the advantages of using task-based parallelism, is that we schedule the task and fetch the data, but the task doesn't run until the data arrives. Right. And we overlap tasks with fetching data. That way we always have something that's running, and we keep the task queue full. We don't need to worry too much about how long it's taking data to arrive, as long as we have something that can be computed now. Yes, but once you run out with data which is available to you, basically your node is not doing any computations but just waiting for data to arrive, right? And it might happen if you have really massively parallel, and I mean it's kind of difficult stuff to schedule it very efficiently, so it will be all your nodes will be always busy, and I think it's the main problem why it doesn't scale. I mean, why the scaling decreases once you go to really a highly number of nodes, right? Yeah, and that's the problem. It's a problem of expressing enough parallelism to keep all of your nodes busy. And as I mentioned in the previous slide, here we only have a few nodes. I can't remember what the exact distribution was, but I think we had about 16 tiles per node. And each of these tiles can only compute so many contributions at one time. And we have 64 threads that can be doing work. So obviously, dividing 16 units of work among 64 threads just isn't going to scale properly. And that's the problem here. So it's a problem of granularity. And that's why a smaller grain size actually scales much more efficiently. Yeah, I think. And you're absolutely right. It's very challenging to keep all of these processors busy when you're worrying about data movement. But again, task-based parallelism helps ease the problem of data movement and ease the problem of overlapping communication and computation.
Yeah, okay, thank you. So are there any other questions from our group or from any other attendees? I don't see anything here. No questions? Okay, so since there are not any other questions, so thank you very much for a very nice presentation, Justus. So thank you.
All right, thank you.
Thank you.